Welcome to Math All-Star, a math program dedicated to gifted students. Today's topic is square numbers. Every student knows what is a square number. It sounds simple enough, but there are still many interesting and challenging problems waiting to be explored. As we mentioned many times, competition math is not about exotic formulas. Instead, it is about how to apply basic knowledge in an appropriate and flexible way. Square number is no exception. Here are all the basics which are our weapons to tackle many square number related problems. First, a square number can only end with 0, 1, 4, 5, 6, or 9. It is obvious, isn't it? Yes, it's not fancy at all. Secondly, the square of an even integer must be a multiple of 4. This is a modular arithmetic expression. It basically states the remainder of n squared when being divided by 4 is 0. Or, in another word, n squared is a multiple of 4. This conclusion is intuitive as well. The proof is written in arithmetic expression. Don't worry if you are not familiar with it. If n is odd, when n squared is divided by either 4 or 8, its remainder is always 1. For example, the first few odd perfect squares, 1, 9, 25, 49, etc., all satisfy this property, don't they? This is an important and very useful conclusion. Again, the proof is written in modular arithmetic. It is also possible to prove it using basic number theory expressions. Before we move on to discuss some examples, here's a quiz. Can the sum of two squares has a remainder of 3 when being divided by 4? Think about it. The answer is no. This is because when a square is divided by 4, its remainder can only be either 0 or 1, as we just discussed. So sum of two such remainders can only be 0, 1, or 2, but never 3. Do you agree? These basics are all we need to solve many interesting and challenging problems. Take a moment to review them before continuing. Here is our first example. If the tens digit of a square is 7, what is its unit digit? By guessing and checking, we may find 6 is a possible choice because 576 is a square of 24. The question is, are there other possibilities? If yes, find them all. If no, how to prove 6 is the only choice. This problem can be solved by the following analysis. A square number can only end with 0, 1, 4, 5, 6, or 9, right? Because its tens digit is 7, we have the following candidates for the last two digits: 70, 71, 74, 75, 76, and 79. Now, how can we eliminate some impossible cases? Do you still remember that a square number must be either a multiple 4 or multiple of 4 plus 1? To verify whether a number satisfies these two conditions or not, it is sufficient to just check its last two digits. Hence, we find among these candidates, only 76 is a possibility. Meanwhile, as we have already found a perfect square 576, which is ending with 76. Therefore, we can conclude its unit digits must be 6. In fact, we can extend the previous example to the following fun facts about a square number. First, if n is odd, then n squared must end with an odd digit. This is obvious, but more interestingly, we can assert its 10th digit must be even. Second, if n squared ends with 6, then its 10th digit must be odd. On the other hand, if n squared's 10th digit is odd, then its unit digit must be 6. In fact, the previous example is a special case of this fun fact. Do you see it? Finally, if n squared's unit digit is neither 4 nor 6, then its 10th digit must be even. Have you ever noticed these interesting facts? They can all be proved using a similar approach as we did for the previous example. Here we just prove the first fact. The remaining conclusions will be left as your homework. Because n is odd, n squared must end with an odd digit. This is obvious. It follows that its unit digits must be 1, 5, or 9, because a square number cannot end with 3 or 7. Meanwhile, we know n squared must be a multiple 4 plus 1, or equivalently, the quantity of n squared subtracts 1 must be a multiple 4. Considering its unit digit must be 1, 5, 9, it is not too difficult to verify its 10th digit cannot be odd. Let's review a few more examples. The first one is to determine the number of square numbers in this infinite sequence. Think about it. The answer is 1. Only number 1 is a square. All other terms cannot be squares. Why? Obviously, all terms are odd. Therefore, if a term is a square, it must be a multiple of 4 plus 1. Equivalently, subtracting 1 from that number must be divisible by 4. However, except the first term, all the following terms end with 11. Subtracting 1 will result in a number ending with 10, which cannot be divisible by 4. Therefore, they cannot be squares. Do you agree? The second question is similar to the previous one. How many terms in the sequence are squares? By utilizing the answer to the previous question, we can assert only the first term is a square. This is because every term in the sequence can be written as a product of 4 and a corresponding term in the previous example. Because 4 is a square, therefore, in order to make the product a square, the other term must be a square, isn't it? But we know there's only one term in the sequence of the first example is a square. Consequently, there's only one term in this sequence is a square. The question is a bit challenging. How many terms in this sequence are squares? By guessing and checking, we find 144 and 1444 are squares because the former is a square of 12 and the latter is a square of 38. In fact, no other term is a square. For this, we are going to show a square number cannot end with 4444. There are different ways to prove this. The first method is to examine its remainder when being divided by 4. For this, we rewrite such a number in this way. When dividing this number by 4, we get this result. The first term is an integer multiplying with 2500. The second term is 1111. It is now clear that the last two digits of this number must be 11. We know it is impossible to be a square, correct? We can also examine its remainder when being divided by 16. In this case, the remainder is 12. It can be shown that when a square number is divided by 16, its remainder cannot be 12. You will need to prove this conclusion in your homework. Here, because it cannot be 12, therefore any number ending with 4444 cannot be a square number. Now let's apply what we have learned to solve some indeterminate equations. Indeterminate equation is a popular subject in math competitions at all levels from AMC 8 to IMO. Square number properties may come handy to tackle such equations. Here is one example. How many integer solutions does this equation have? The answer is none. To show this, let's take mod 4 on both sides. On the right side, the remainder is 3 when 2015 is divided by 4. However, as we have shown earlier, it is impossible for a sum of two squares to have 3 as the remainders when being divided by 4. Do you agree? Okay, here's another example. Can you solve this equation in integers? The answer is still 0. Why? If there's one solution, then 5x must end with either 0 or 5. It follows that 5x plus 1 must end with 1 or 6. Multiplying it by 3 results either 3 or 8 as its ending digit. However, no square number can end with 3 or 8, right? If so, we conclude this equation does not have any integer solution. This concludes our discussion today. Please review all the examples if necessary to ensure you fully understand all of them. Homework can be found on the website. Some problems are challenging, but they can all be solved by the simple properties we have discussed today. Have a try. Feel free to get in touch if you need any help or have any question. Thank you.